All right, gang. Stat 1150. What I have learned in my many years of teaching statistics is that the central limit theorem is difficult for a lot of students. So what I'm going to do, there's going to be 3 additional videos. There's going to be central limit theorem problems part 1 that we're obviously working here. There's going to be a part 2 and there's going to be a part 3. Depending on how quickly you pick up on this stuff, I guess dictates the intensity by which you need to watch these videos. I can't even say that without laughing. But what I want to do, a couple things. I want to primarily, the previous video kind of taught the concept. It taught kind of the theory behind how we work the problems. But in the next 3 videos, or at least the next 3 videos, yeah, I just want to work some problems for you and see if we can kind of tie all of it together. Again, if you're sitting there and you watch the first video and you're thinking, man, this central limit theorem for means is insane stuff and I don't understand it. What I would tell you is that kind of means you're normal. That just students, semester in, semester out, year in, year out, seem to struggle with central limit theorem. I'm about to lose my voice, so that's why it's kind of cracking. So bear with me on that one. So one more thing I'm going to do, and not only are we going to do the problems, but I'm going to teach a little bit, just throw some things in that you'll need to work your online course management homework assignment. And another thing I'm going to do is I'm going to use different calculators. Now, and I'll illustrate that throughout the video. I'm going to use this calculator, and then I have a calculator on my computer that I'm going to work that comes up with a different format when we use normal CDF. So depending on the type of calculator you have, things may look different than, look completely different actually, than what I do on my calculator. So guys, enough talking, let's get busy. So we're talking about some emissions for a particular kind of car vary with the normal distribution, mean 2.9, standard deviation 0.4. Now, when you're given the information from a population, these values here are known as parameters. And for this particular problem, the mu 2.9 and standard deviation 0.4 are given with this notation. Now, in teaching this class, students struggle with x bar versus mu, and Sx, and many books just use S for this, and Sx versus sigma. Guys, we can draw a line down the middle. This notation, let me get my big old hand out of the way. This notation over here represents things we call parameters, and they describe values in populations. This notation on the left-hand side over here, we call those statistics, because it's x bar and S of x. And these represent values from a population. So what is the probability that a randomly selected car has a carbon monoxide emission level greater than 3.2? Well, since we're talking about a randomly selected car, the value that's referenced there would be x bar. So again, just remember, keep it simple here, kind of the KISS principle. If the number is describing a population, the broader group of scores, the larger group of scores, our population, then we have mu and sigma. If it's talking about the values from a particular sample size n, then these are given as a statistic each, and they represent measurements that come from a sample. All right, so let's work the problem. So what's the probability that a randomly selected car, so guys here, the sample size is n equal 1, has carbon monoxide emission levels greater than 3.2? Well, guys, since we're talking about n equal 1, we're just talking about a single score. So really the whole central limit theorem doesn't apply because the central limit theorem has to do with the distribution of sample means. It has to do with problems where we take more than one at a time, like I discussed back in the initial video. Now guys, if you're trying to skip over that first video, I think it was like 55 minutes. It was probably pretty boring. But guys, you just got to stick with it. You know, life is not all, roses, candy, wine, and nice bourbon. You know, sometimes we got to just suck it up. So you gotta watch that the first video. All right, so let's work this one. So guys, really all I have to do here is just grab my calculator. I could do this problem either with calculus or a calculator. Trust me. I think you want to choose the latter. So go to distribution, go to normal CDF. Since I want greater than 3.2, I'm going to start with 3.2 and go up to infinity. And our mean is 2.9. And our standard deviation is 0.4. So these are straightforward problems. Guys, probability, we typically round to 4 places. Don't get too caught up into that. That's just kind of the way I round, so it'd be 0.2266. Whatever the rounding procedure on your online course management system, probably my math lab, round according to what they want you to. All right, gang, let me show you how another type of calculator with a different operating system may work. So let me get out of this and bring up this. All right, so with this calculator, we're going to see things a little bit different. So we still go to second function distribution, and we still go to number 2 normal CDF. But you'll notice now you don't have a left parentheses and you're putting things in a string from left to right. You really kind of are, because what you put first in the string of left to right goes there. What you put second goes here. What you put third goes there. What you put fourth goes there, and so on and so forth, as you'll see in just a second. So guys, what went first was 3.2. Hit enter. Upper was E99. Enter. Our mean was 2.9. And our standard deviation was 0.4. Now watch what happens when we paste this. We paste it back into the home screen, and it actually gives us the thing that we saw before from left to right. But if you're struggling learning the calculator, getting to this point can sometimes be a little crazy. So guys, get the same answer, 0.2266. All right. Next problem. Now, this is a problem where the central limit theorem kicks in, because we're not just looking at one car, we're looking at 17 cars. So when we think about 17 cars, how do we want to represent those 17 cars? Well, we want to add all 17 scores up, divide by 17, and get a sample mean. So now we're looking at the probability that the average measure of these 17 cars is less than 2.75. So in the sampling distribution, which by the way is going to be a lot taller and a lot skinnier, a lot narrower than the parent distribution that we're drawing from. And I'll try to illustrate that in just a second on the calculator. So what we want to do here is we want to work the problem just as we did before. So we're still going to have normal CDF. But guys, now we're looking at less than 2.75. So less than 2.75 means we start with negative infinity and come all the way over to our sample mean. So because of that, we got to put things in the calculator just a little differently. So negative E99 we start out with. We couldn't start. I see a lot of students sometimes that'll start out with positive E99. Guys, this is the lowest number. E99 represents positive infinity. It doesn't get any bigger than that. How can you start with the biggest when what you start with is the smallest? It can't happen. Okay, so negative E99 up to our mean, which is 2.75. Our mean stays the same of the parent distribution at 2.9. But our standard deviation switches to what we call a standard error. 0.4 divided by the square root of the sample size. Well, guys, the sample size in this problem is 17. So our answer is 0.0610. Now, how would you work this problem if you had the other calculator? It's probably going to drive those of you insane that don't have the other calculator, but just bear with me. Well, since we're starting lower than, our left bound has to be negative infinity. It's just goofy as all get out if you put positive infinity there, because the left bound is the value furthest to the left, and positive infinity is the value, or at least a symbol for the value, furthest to the right. So our upper is 2.75. And our mean is 2.9. And our standard error is 0.4 divided by the square root of 17. All right, so guys, be careful with the division sign. Be careful with your parentheses. That can sometimes make things go kind of crazy. All right, gang, so you'll see we get the same answer at 0.0610. Now, I told you earlier that I wanted to illustrate something, and I want to just stop now and illustrate that while I'm thinking about it. Okay, let's say, for example, let me turn over, and I want to kind of validate a statement that I made. All right, what is the difference here? Let's say we have a mean of 100, standard deviation 10, but we want to draw samples of size 20 from this distribution, analyze the distribution of the sample means, and compare this distribution with this distribution. Now, what did I tell you would happen? This distribution right here will be taller and narrower. Why? Because the standard error versus the standard deviation. Up here, when we're talking about our parent population, we just talk about the standard deviation. But when we come down here and start taking things out 20 at a time and look at the distribution of the sample means, then we start talking about the spread in terms of the standard error. Now, the standard error, remember, is the standard deviation divided by the square root of n. Well, guys, go back to 5th and 6th grade and think what you, or at least recall, what you learned about fractions. When you increase the denominator in a fraction, what happens? This value gets smaller, doesn't it? So it doesn't matter what this value is right here, and let's just hold it to be 10. As this number gets bigger, let's just keep the square roots a nice number. 10 divided by 2 is 5. 10 divided by 3, 3 1/3. 10 divided by 4, 2.5. 10 divided by 5, 2. What's happening to these values? They're getting smaller, aren't they? That's why we say that the distribution gets narrower, because the measurement that we are using to define the shape of the distribution, the variability within the distribution gets smaller because of this whole standard error dynamic, or standard error dilemma for many of you. Now, let's just take a look at that. Kind of a cool feature here that we can do on our calculator and do some graphing. All right, so let's clear out some things. I've been teaching some Math 1700 here, so let's clear some things out. And I want to put in something called normal PDF. And this is what you use. You don't use normal CDF if you want to graph. You use normal CDF if you want to get a probability or proportion or percentile, things of that nature. I call it the P key. But if you want to graph, you use the normal PDF, the normal probability density function. So I'm going to put in x because we have to be a function of a random variable. And I want to look at the distribution with mean 100, standard deviation 10. Okay? Now, a little trickery here. I'm going to go ahead and set my window up to 3 standard deviations below the mean, to 3 standard deviations above the mean, because that gives us 99.7% of our distribution. And then I'm going to come in here and set that 1, and I'm going to set this whatever. It really doesn't matter because I'm going to show you an option on your calculator that allows you to adjust the y given certain x values. So it doesn't matter. As long as this number is smaller than that number, this next function will work. Now, if you do something wacky and put in a 5 there and a 2 there, then you're going to get an error. This number, the min, has to be smaller than this number, the max. The y min has to be smaller than the y max. Now, if I go to zoom fit, this is the key in the calculator that will adjust the y window based on the x values that we give it. And that just did a horrible job. Oh, I know what I did. I pulled a bozo. So let's go zoom fit. I hit graph. I should have hit enter. I was wondering what in the world's going on here. I made a mistake. Okay, so that's the parent population. That would be the distribution with mean of 100, standard deviation 1, if we pull out samples of size 1. That's what the distribution of the measurements would look like. Now, what would happen with this distribution? Well, what we've learned in previous videos, it would make sense we'd use the same command. Still a random variable of x. Still the mean of 100. Why? Because mu is equal to mu sub x bar. The mean of the population is equal to the mean of the distribution of sample means, which we're examining right here. However, standard deviation isn't the same, is it? We get into this dilemma. It's pretty easy. It's not that hard. It'd be kind of hard if you had to do all this by hand, but since we have a calculator, we can just put in 10 divided by the square root of 20. 10 is the standard deviation of the population. 20 is the sample size, right there. Sigma over the square root of n, okay? Now, let's graph this. Now, the graph's going to look really goofy and wacky because we don't have the scale set, but I want to show you how much taller and narrower this distribution is than this one. In fact, it's so much taller and it's so much narrower, we can't even really get a good view of it. So what I'm going to do is I'm going to go in and tinker with my window a little bit, and I'm going to go up on my Y max to about 0.07 and see what happens. This should actually give me a pretty good picture. So there's the parent population, mean of 100, standard deviation 10. And here we go. Well, I didn't even go high enough, did I? I'll tell you what we can do. Let's just use the same thing. Zoom, fit, hit enter, not graph. And it'll set the window for both distributions. Can you imagine back in the old days when Had to do all this by hand. Be kind of crazy, wouldn't it? So the second distribution, again, is going to be taller and thinner and narrower because that's the way that the sampling distribution behaves. And it really helps us in inferential statistics. All right, gang, let's go on and do some stuff. All right, calculate and interpret the z-score for a car. A car. N equal 1. From the previous video, I told you that if we have just one car, we use the z-score formula that we've seen before. X is the measurement of the car. Mu is the mean of the population. And sigma is the standard deviation of the population. Now, guys, this should be a pretty easy problem unless you do something wacky. Now, I have seen students before do this. And they get the wrong answer and like, well, Dr. Darber, I did the same thing you did, but my calculator doesn't like me for some reason, and it doesn't give me the right answer. Well, no, you didn't do the same thing that I would do. Guys, we have to make the calculation in the numerator before we divide by the 0.4. So you had a big old major order of operations issue here. So if you wake up tomorrow and you think, you know what, I just want to drive myself insane. I want to get all my statistics problems wrong. I just want to get everything wrong. I just want to flunk. Do that. It'll work every time. But if you want to get the right answer, then put it in correctly. Put parentheses around the numerator and the denominator. Now, since we've only got one thing going on in the denominator, I don't need a parentheses down here. But if I have more stuff down here, which I will in just a second, I would need to put it in parentheses also. So, guys, the z-score is 1.5. I tell you also to interpret. The interpretation would be this. A car with emission level of 3.5 is 1.5 standard deviations above the mean. A car of 3.5 is 1.5 standard deviations above the mean. All right, 15 cars are selected at random. That tells me I can no longer use this formula. I have to use the z-score formula. And just keep you honest, and we're going to put everything in parentheses here. I have to use the z-score formula that is appropriate for this type of problem. This would be like me working in the house and sending my wife down to get a screwdriver, and I need a straight screwdriver, and she brings me a Phillips screwdriver. It's a screwdriver. It's a z-score formula, right? But it's the wrong screwdriver for the job. Guys, you got to use the right tool for the job. And the right tool for this problem is this z-score formula. So where I'm looking at here is the sample mean. So we want to look at 3.5 minus the population mean, 2.9, over sigma, which is 0.4, over the square root of the sample size, which is 15. Now, gang, you got to be a little more careful here. So 3.5 minus 2.9 divided by, now in the parenthesis, in the denominator, I got more stuff going on, so I have to kind of partition it out and do things this way. It is so, and I'll go ahead and tell you the answer. The answer is 5.81. Let me go back and show you what is so tempting to do, and I see it happen all the time when people don't know what they're doing. They get problems wrong. They put in 3.5 minus 2.9. They're real proud of themselves because they put the numerator in parentheses, but then they don't carry it through. and they come in and do something wacky like this. Now what this is going to do, your calculator is going to take that subtraction. It's going to take 3.5 minus 2.9, and then it's going to divide by 0.4. And then it's going to recalculate the answer. Then it's going to take that and divide again by the square root of 17. That's not what you want. You want that operation done. You want this operation done, and then you want to take this number and divide it by that number. That's not what happens here. This actually does a double division. You can see you get 0.36, and I've had students say, Dr. Darber, I did the same thing you did, and I got a wrong answer. My calculator doesn't like me. No, you're not paying attention to detail. You're not putting the parentheses around the denominator like I'm telling you to. So 5.81. So our interpretation here would be a sample mean of 15 cars is 5.81 standard errors above the mean. A sample mean of 3.5 from 15 cars is 5.81 standard errors above the mean. Why do we say standard errors? Because we have to consider the standard error as the variability in the sampling distribution as compared to the population standard deviation as the variability in the parent distribution. So a whole lot of messiness on there, but it looks horrible now, but it kind of made sense working through. At least I think it did. All right, what sample size results in a standard error of 0.5? Well, let's go to the standard error definition. The standard error is sigma over the square root of n. So what sample size? So that's going to be our unknown. N is a perfectly good variable, so I'm just going to leave it as n. Results in a standard error of 0.5. So I need this to be, I'm sorry, it isn't 0.5, it's 0.05. Now we're going to use this information from the problem because this E says it's still part of the first problem. So 0.4. So our problem becomes 0.05. 0.4 over the square root of n. Now guys, I'm going to use a trick here, and the trick is something that you learn in dealing with proportions. Anytime you have a fraction equal a fraction, you can switch the values on the diagonal. Let's just think it through. Let me just show you why this works. I think we would all agree that 1/2 is equal to 5/10. Let's switch these. So if I put a 10 up here and put the 1 down here, it's 10 over 2, still 5 over 1. Well, it is, because we can do that. Switch the 5 and the 2. You'd have 1 over 5 is 2 over 10, same thing. All right, so what I can do right here is I can switch these and quickly make this the square root of n over 1 equals what? 0.4 over 0.05. Take the 0.05, which is in the numerator, make it the denominator, which I did. Take the square root of n, it's in the denominator, move it up here, make it the numerator. Square root of n over 1 is just the square root of n. Now I'm going to square both sides. So on this side, I just get n equal. And on the right side, I get 0.4 over 0.05 quantity squared. Well, guys, I need my calculator for that. I could do it by hand, but I don't want to. Okay, everything look okay? All right, so our sample size would be n equals 64. All right, gang, let's get through this next problem pretty quickly. This video is taking a little longer than what I thought it would. Waiter believes the distribution of his tips is positively skewed. Uh-oh, when you read positively skewed instead of normal distribution, what's that tell you? We need our sample size to be large. And what does large mean in this textbook? approximately 25. Some textbooks will tell you 30. In fact, that's kind of the rule that I grew up with, is that large meant 30. But some of the books are finding that sample size of 25 suffices. I'll tell you what I'll do. I'll probably give you an illustration next week on the central limit theorem using something called stack crunch. It's kind of cool. It shows you the difference in the distributions with different sample sizes when you start out with something that's not normally distributed. So anyway, let's go ahead and work the problem. What is the probability his next party will tip him more than 20 bucks? Now, undoubtedly, students will pick up their calculator and they'll come to normal CDF and they'll start punching buttons. And I'll say, well, you can't do this problem. And they're like, well, hell, I can. I just typed it in and it worked. Yeah, well, it doesn't work because it's a positively skewed distribution. You don't have a positively skewed CDF. You've got a normal CDF. So for this to work, we would have to have a normal distribution. We don't. We've got a positively skewed distribution. So what's the probability his next party will tip him more than 20 bucks? You can't do the problem because you don't have a normal distribution. What is the probability the average tip for his next 4 parties will be greater than 10? Well, you need a sample size large to turn this positively skewed distribution into a normal distribution. Not big enough yet. You got to get this sample size up to around 25 or 30 before this positively skewed distribution will become normally distributed. What's the probability of the average tip for the night for 32 parties? Okay, now you're getting into a sample size where the central limit theorem kicks in. So what we'll do here is we'll do normal CDF less than 12, which means I have to start with negative E99 up to 12. The mean of the distribution. The standard deviation divided by the square root of the sample size. So gang, if we can put this in our calculator without doing something wacky, and we should be able to do that. What is it, 9.60? Okay, what we got now? 5.40. Square root of 32. All right, so we get a sample, a probability of 0.9940. All right, well, if you've got the other kind of calculator, just very quickly, how would you work this? Well, you'd use normal CDF. Normal CDF is right there. First thing you'd have negative E99. There's no need to retype that. The upper is 12. The mean number of tips was $9.60. The standard deviation becomes the standard error because we have 32 parties. Paste, and you'll see we get the same answer. All right, 0.9940. Guys, that's it. I'm done. Take care.